Video 2 for week 2 of remote learning. We are now on page 14 of notes 3. And again, I've got another little joke for you. So pause the video if you ever need more time on the notes. All right, so here we go. So the third law of thermodynamics says the entropy of a pure crystalline substance at absolute zero is 0. So if we think of a cube of salt, for instance, NaCl, if it is at absolute zero, there is no movement of any kind. It is perfectly organized. It is not random. So there is no entropy in that system. Once we increase the temperature of that solid, then that would increase the entropy because the molecules would start, or the atoms would start moving around and then become disordered. Okay, so we have a delta, we have S for entropy. The little 0 there is for standard entropy. So the standard molar entropes is something we look up in a table of values, okay, at 1 atmosphere and 25 Celsius. Sometimes the little 0 is called naught, like it's all for naught. Anyway, that's a standard temperature, or sorry, standard conditions. So we call that S naught. Okay, so the standard molar entropy is not 0 for elements. So I'd like you to think about, when would it be 0? Kind of answered it already. Okay, so for heat of formation, you may recall, standard heat of formation for elements is 0, but it is not 0 for the standard molar entropy. I'll answer that question later on in the video. Okay. All right, so in general, the entropy of gases is greater than the entropy of liquids and greater than the entropy of solids. The S naught increases when you have increasing molar mass, and S naught increases with increasing number of atoms. So again, pause the video and think through that. Why would increasing molar mass and number of atoms increase the entropy? Very simple formula to determine delta S naught. That is products minus reactants, so very similar to what we saw for delta H naught when using the heats of formation. So again, we would look up the S naught values in appendix, I think it's appendix 2 actually in your book. All right, so some practice problems for you. So use this previous formula here to solve for these two. So please pause the video and do those two problems. Here are the answers. For A, it's 92.2 joules per mole Kelvin. It makes sense that that is a positive number because we increase the number of particles for that reaction. That means we have an increased number of microstates, increased amount of randomness. Part B was negative, 88.6 joules per mole Kelvin. Again, it makes sense that delta S is negative. We have a decreased number of particles and a decreased number of microstates, so decreased entropy. Now I want to point out that if the water that was a product had been liquid instead of gas, the entropy would have decreased even more because the entropy of liquid is lower than the entropy of gas. Okay, so all of this leads to, again, the spontaneity of a reaction. We use something called Gibbs free energy to predict whether a reaction is spontaneous. So here's a picture of Gibbs. Oh, that's the wrong Gibbs. That's Mr. Gibbs. Okay, here's Gibbs, Josiah Gibbs. All right, so here is the story. If the delta G, that's the Gibbs number, is negative, the forward reaction is spontaneous. If delta G is 0, the reaction is at equilibrium. We will talk more about equilibrium later, but it's not good. The reaction doesn't go forward or reverse. Okay, if delta G is positive, the forward reaction is non-spontaneous. We could also say if delta G is positive, the reverse reaction is spontaneous. So if we think of liquid water becoming gaseous water, the reverse would be gaseous water becoming liquid water. So many reactions can be reversed. Okay, very similar formula to what you had for delta S naught. We do products minus reactants. We need to include the coefficients here for the products and reactants. Again, you can look up these values in your textbook. I think it's Appendix 2. All right, so please solve for the delta G naught of the reaction here. Pause the video. Here's the answer. Okay, now we want to think about whether this reaction is spontaneous. Again, we are looking at the sign of delta G. It's negative, so yes, the reaction is spontaneous at standard pressure and temperature. Okay, now another way to solve for delta G is using this formula. Delta G naught equals delta H naught minus T delta S naught. Okay, T is 298 Kelvin, which of course is 25 Celsius, and that is the standard free energy of reaction. Okay, so that little, the little zero sign there is for standard temperature. Okay, now if it is not a standard temperature, we would use this other formula. So there's no little zeros here because it is not at standard temperature, but we do, again, need to include the temperature in Kelvin. So we just solve for Kelvin before we plug it in. Okay, now here's the story. We can look at delta H, T, and delta S to decide if delta G is going to be negative or positive. So again, I'd like you to pause the video and give this a think. Look at the equation and decide on each of these. Okay, so if delta H is negative and delta S is positive, will delta G be negative or positive? So pause the video and see if you can figure out each of these. Now the answers to these are very relevant to AP Chemistry. So if you can figure these out in your head without actually calculating any numbers, those are some really solid skills for AP Chemistry in a couple years. Okay, so here it is. If delta H is negative and delta S is positive, delta G will be negative. The negative sign that's in front of the T delta S, that is going to be positive if delta S is negative. Is positive. Oh, it's going to be negative if delta S is positive. So then delta G will have to be negative. Okay, so give those a think. If your reasoning was not correct, go back and really think about it. Nothing can replace the thinking. I can show you and I can make it sound easy, but you have to sit and think about it if these answers make sense. All right, so here are some other ways to think about this. Okay, in an exothermic reaction, that means delta H is negative. If entropy increases, that means the reaction is spontaneous. Endothermic, that means delta H is positive. If entropy decreases, that means it's non-spontaneous. So for this second one, right, it needs a reaction that's endothermic requires heat. If entropy decreases, that's like opposite of what the universe wants to do. So that reaction will not go forward without some additional help. It's not spontaneous. Okay, now if it's exothermic and entropy decreases, those two are kind of opposite of each other. So exothermic is going to produce heat, but entropy decreasing is opposite of what the universe wants to do. So in that situation, the reaction will be spontaneous only when the temperature is really low. That means that your second part of the equation, the minus T delta S, would have to be really small to be spontaneous. Okay, if it's endothermic and entropy decreases, that negative T delta S would have to be really large to overcome the endothermic delta H, the positive delta H. So again, think these through and see if they make sense. You have to really use your logical reasoning skills here. Okay, now another version of this, however, I want to say, you can also just calculate delta H if you have those values. So you'll be doing some of those practice problems in the web labs. So here are some more, here are some actual reactions for you to think through, examples of spontaneity. So I would like you to assign a delta H, delta S, and delta G for each of these reactions. You can see that they are opposite reactions, so the first two are opposite of each other. The second two are opposite of each other. So think these through. Try to assign a positive or negative delta S, delta H, delta S, and delta G for each of these reactions. I don't think I have a slide for the answers for this, so I will try to post those somehow. Oh, I do. Just kidding. All right, so I have a couple more videos that I'd like you to watch that will help you understand this topic. Okay, so an earlier question we had is entropy for elements is at 25 Celsius, not 0. When is entropy 0? Again, at absolute 0. Okay, so no disorder there. Okay, and I think, I thought I had one more joke. I guess not. Well, good luck, kids.